people are doing as well.
Got it. Right, simultaneous. Now, I just want to give a bit of background on what you're setting up. So, for the benefit of the listener viewer, a couple of things. I have a bit of an obsession with simultaneous equations because, firstly, I taught it rubbish for years. And the way I taught it rubbish was I would teach it as if it was a complete procedure from start to finish. And I would just go over example after example after example. Sure, they start off easy, but I would take kids from the start to the finish again and again and again, and kids were going wrong, and I couldn't figure out why and where they were going wrong. And then I interviewed Chris Bolton for my podcast the first time he'd been on the show, and it was a 2-hour podcast, and I asked Chris one question, and that was, how do you plan a lesson? And he talked me through in great detail, and I believe you've listened to it.
Yeah, I have, yeah.
How he planned a sequence of lessons, and he describes it as his best ever sequence of lessons on simultaneous equations. And he broke it down, I think, into 13 individual skills, and he hammered each of those skills using kind of a model of deliberate practice, then knitted it all back together. And I thought to myself, that is it. That's game over for me. That is how I'm going to teach simultaneous equations. So I was very happy with myself there. And then I went to Maths Conf 14 I think it was, in Kettering. And Mark McCourt said, you've got to go and watch Bernie's session. And you were doing simultaneous equations. And you were doing it, and I spoke about this on the Conference Takeaway podcast that I recorded straight after it. And you were doing it with like flipping 7-year-olds or something absolutely mental like that. Like
5-year-olds and 6-year-olds.
Don't be telling me this. Don't be telling me this. So, and it was a completely different way of doing it. So I've a million questions, but before we dive into them, how do you do? Yeah, what's the age group that we're starting with, and how does it all start? This kind of notion of equations, simultaneous equations, and so on.
Okay, so this is the one I showed at the conference. This is a poor picture of this one over here.
Okay.
And I set it up where I just gave adults those equations there,
Yes.
and I didn't let them know about this. And then we
Yes.
showed them a little child of 5 going, solved it.
And I should say, like, this one is one you'll really have to watch on the video.
Yeah,
But
yeah.
we've essentially got, it's kind of like a puzzle grid, right? We've got a 3x3 grid, and we've got 2 rectangles in a car equals 5, 3 kind of fish things equals 6, and so on. And we've as teachers, we know that these kind of hidden simultaneous equations in there, but crucially, there's no letters, there's no equations or anything like that. It's just kind of like a picture puzzle for kids to try and solve. But yeah.
Okay, which goes, sorry, I'm thinking of, you asked me, is there a connection to how Chris teaches this?
Yes.
And the answer is there is one connection.
Okay.
So I'm just going to backtrack a little bit. From a very early age, we're going back to those number bonds, is that children learn that you can solve some equations, definitely, and some you can't, except they don't call them now. And I had particularly visiting a school recently, I had a complete car crash of a lesson with this because the children didn't know these ideas.
Right.
So when we're doing number bonds for 5 with young children.
Now the cups are out here.
The cups are out, you've got a red cup and a blue cup.
Okay.
The signal is that there's different quantities in here.
Okay.
Because they're different colours.
The colour, right, okay, fine.
So all they know is that there are, and I'll come back to this after this one in a minute,
Sure,
I need to show you this first, is there are 5 cubes in here.
5 cubes.
In there, but I'm not going to tell you how many.
But I know the different.
You know they're different, okay?
And they're all in the cups.
Yes. So when I asked these year 2 guys, not my kids, I've gone to visit, okay, do you know how many definitely in there? Yes. Okay. So how many do you say in there? There's 3 and 2. Okay. Anybody else definitely know? There's 4 and 1. Okay.
Yeah, okay.
And they had never played with these ideas, so they didn't realise that actually I can't definitely tell you the answer to that.
And that's a big thing, right?
It's a big thing, but we do this with reception age and nursery a little bit as well. Can you tell me definitely what's in there?
The idea of not definitely knowing something in maths is massive, right?
Absolutely, and it gets overlooked a lot. We're so busy solving things and finding things, we forget the fact that from a very early age, these concepts, and I explain to teachers how important this is later.
Yeah.
You can't tell me definitely. Okay, and then we think mathematically. Can you give me a list of possibilities?
Okay.
5, 0, 4, 1, and we're back to our number bonds and that.
And is this, am I right in saying that this plays upon this idea of hiding things as well? That you
it forces, hide a lot of stuff.
It's good that.
And puppets getting it wrong.
Okay.
It's very important.
So we're using this for the concept that you don't definitely know something, but we start to list possibilities.
If I give you this.
So now we've got 2 blue cups and 4 counters.
Yeah. Can you tell definitely what's in there. I
can.
definitely can.
Definitely
okay?
can, yeah, that's nice.
And sometimes, I don't tend to do this to young children.
Ooh. So now we've got 5 counters and 2 blue cups, so this would be kind of unsolvable, right?
It's unsolvable, yeah.
And you'd possibly bring that in?
Yeah, and some kids, very young children, will tell you to chop that down the middle.
Really?
Okay, so you've already, at
That's
the very
interesting.
beginning, you've got the idea that there can be one solution, there, no solution, and multiple solutions.
I'll tell you what, this is similar to Chris's start, right?
Yeah,
because
yeah,
Chris
no,
would
yeah.
focus on
That's why I wanted to bring that in.
what is an equation, what is
Yeah.
simultaneous,
Yeah.
what's solvable.
Yep.
But the twist is you're doing this with 5-year-olds.
Yeah, yeah,
is that
yeah.
right?
But you
Slight
have to
difference.
if
Yeah,
they're
yeah.
going to have a real number sense.
Got it, got it.
Again, we hide things in there, so, and the other thing, sorry, I didn't do was, okay, again, imagine you're 4 years old, Craig, shut your eyes.
Okay,
Hang
yeah.
on, before you close your eyes.
Okay.
How many cubes are there on there?
5 cubes.
Okay, good. Now, with a younger child, I might have to put in a pattern like that for them to
Yeah,
spot
yeah,
it.
yeah.
Okay, right, close your eyes, Craig.
Okay, yeah, go on.
Okay, close your eyes, close your eyes, close
Yeah.
your eyes, close your eyes, close your eyes. Open your eyes. Okay, I've hidden some underneath here.
Okay.
Do you know how many I've hidden underneath
So
there?
there's one left out that I can see, so 4 is
Yeah,
under
and
the
they
red
might
cup.
use their hands and do
Yeah,
things like
okay.
that. But hiding things again makes
Yeah.
things happen. Solves it. That's solving equations. That's a
And I'll tell you what.
you just solved an equation. There,
Yeah.
Really, but in a very young age.
There's a few things I like about that.
Yeah.
I like the visual aspect,
Yep.
and I'm being increasingly sold on this throughout
Yeah.
throughout this conversation. I like the kind of reward that they get.
Yeah. Oh,
of
they
being, like,
jump with joy. Yeah.
and it's convincing, right? Because there's one thing me saying to them that is the right answer,
Yeah.
but it's a completely different ball game if they see it's the right answer,
Yeah.
right? So I absolutely love that. And also, and this is something I've been thinking about lots, and this comes from Dan Willingham and also my conversation recently with Jeremy Hodgson, the power of stories, and particularly,
yeah, absolutely. Yeah.
and the fact that you can, it sounds the most stupid thing ever, but you can tell a story there, right? You can say, I have 5 counters,
Yeah.
now look away, this is now what I've got, what's happened?
Yeah.
And that's far more enticing than either describing it abstractly or something. So I love this. I love this.
And then you just close your eyes, Craig.
Okay, yeah,
Good boy, okay. Okay, open your eyes, open your eyes, open your eyes, okay. Which one do you want to see, Craig, the red or the blue?
Blue, please.
Okay. So can you tell me how many under the red?
Okay.
So you get an element of choice there, what you do
I
as well.
like
So
that.
yeah, look, and for young children, it should be a game, it should be magic, maths should
Yeah,
be,
yeah, yeah.
maths should be fun.
I like that, right, I'm in. So cups have got me to the idea of solvable, not solvable,
Yeah.
but crucially also that some things I don't know for definite.
Yeah. Yeah.
Okay, got it.
And
got
you
it.
then make a systematic list of what they
Yeah,
could be.
and I can make the list.
Thinking mathematically.
Yes,
Okay.
yes.
So then with children here, pretty much this I did with a group of reception, and I did it with a whole group at the board and on a big whiteboard with magnetic things.
4 and 5-year-olds.
Yeah, 4 and 5-year-olds.
Jeez, Bernie, okay.
By the end of the week, they were chasing each other on these, having competitions who finished it quickest. So
okay.
what are ideas in it? Well, this is actually, what I've done is to take from a website. I can't remember the name of it. I'd mentioned them, but I've made the numbers smaller and within their range.
Oh, okay, so we've got
I've
totals.
made sure that all these really are 1, 2, and 3.
Go, right,
Now,
fine.
what I'm really interested in young children is them not doing trial and improvement,
Okay,
but actually using deduction.
okay.
So trial and improvement would be I could put 1 on here and 1 on
Yeah.
here. And I don't really like that, and I try to encourage mathematical thinking.
Okay.
So can you start there?
No.
Because you've got 2 unknowns. Remember, it's like the blue and red cup. You
Yes.
you can't be definite.
Yes, okay.
Can you start here? It's like a blue cup, and a red cup. No, you can't be
No.
definite. So where's the place you can start?
I mean, you could argue that you could do this one because as long as the cups have, it can only be 1, 1 and 2, can't
Yeah,
it?
but you're using trial and
that's-
improvement there. You're beginning to start
because
with a
I
number,
am,
then do
I
another.
am,
Yeah,
of course, I see
So
the
what I
difference,
want
I see
children
the
to do is to be able to look at this and know where to start.
Yeah,
that
I
comes
see
much
it.
later in equations. Like I got all these equations. I remember at A level. Which
Yeah,
one do I
where
start with? What do I do?
You're absolutely right. So the only place I can start for definite is this one here. I've got 3 of the same
now,
thing equals
they may
6.
not have a lot of number facts yet, so they might. This is where the trial and improvement comes in, but they've got the right place. Maybe 1 on each doesn't work.
Yeah.
And this also helps them acquire number facts as well by playing these games and working these out. They're also practicing number facts, but also really thinking mathematically.
I'll tell you what the other thing, before we dive too deep
Yeah.
into this, that I love about this, and I think this is overlooked as well, and it goes back to what we were just talking about and what Chris Bolton does, is decisions in maths are so important, and they get overlooked so much.
No.
And it goes like in secondary, deciding whether to use Pythagoras or trigonometry, deciding sine rule or cosine rule. But here, deciding where to start.
Yeah,
on the grid.
is
That's a
key.
skill, right? If you don't know where to start, you're screwed. It doesn't matter if you're an expert and everything else. So I love the focus that the cups get you to think about the deciding. And now we're on to the kind of next bit of it.
A lot of this comes out of preparing 13-year-olds for scholarships to Eton, Westminster, St Paul's, junior Olympiad maths competitions. It's like, what do I want them doing at 13? What sort of mathematic thinking? Okay, what does that look like at 3, 4 years old? How can I get that in? So that's what we're trying to develop.
Right, okay.
So are there any other guitars here? No. Okay.
Oh, they guitar. I've seen
So
fish
they were
before.
pictures.
Sorry.
My drawing is not good.
Got it. All right, we got
Okay,
three
three
guitars.
fish.
Right, got it.
And then you have to decide where to go next. Then another decision is, and they really pick this up so fast. It's like, I need to go here.
So I have to go there. Yeah.
Okay,
I like
now
it.
if they're not good with numbers, they can have, well, look, I know there's 4 in there altogether, and I've got 2 here.
There.
So again, that's deduction, not trial and improvement.
Of course.
You can use counters to help, and you're developing number facts and fluency.
Yeah, I like this.
So, and they carry on through that.
That's good. That. Okay.
If you write that down algebraically, it looks terrible. It looks like this.
So we've got, for the benefit of anyone still listening.
By the way, I put that one on last on purpose because it's the starting place, so I hid it at the end.
So this nicely looking kind of number picture puzzle can be reduced to 2b plus c equals 5, b plus 2c equals 7, 2b plus g equals 4, b plus g, and it's a horrendous series of 6 equations.
And it's that decision, where do I start? Well, you need to know which ones you can solve. And which ones you can't. And 4-year-old children, 5-year-old can make those decisions.
Make that decision. But you wouldn't, so they're not seeing
no,
this.
No,
they're not going near this at any stage.
I mean, I skipped over these. I can do a lot of stuff like that with green plus blue equals blah, blah, blah. So you can start the algebra there. But
and again, I think this is it's an obvious point, but it's an important point. This is the least important bit of the whole process, the kind of formalising it, right?
Yeah.
But in the past, I know I've jumped to this too fast, whereas all the thinking it's all here.
Yeah, and that was the idea of this one. And it came out of, I think it was the Singapore teachers who visited this country, and I may be doing them an injustice, but somebody visited and said, in our country, our job is to make difficult maths look very easy.
Right, okay.
The English seem to, or the UK, seem to have a skill for making easy maths look very difficult.
Yeah, that's dabbing, isn't it? Yeah.
But somebody did say that, but I can't remember where. So the whole point of this, and it answers one of your questions later, was I don't believe that young children should probably be doing this, but I wanted to prove a point that they could.
Oh, okay, fine. Okay.
So my wife, Dr. Karen McNerney, who's got a doctorate in early years education, is constantly on my case about just because they can do this, Bernie, doesn't mean you should be doing it with them.
Okay.
But it's like, I just want to show that this approach can be done by very young children.
Okay. So what do we, just describe what we've got here, because this I remember...
This is where we started when we first met.
Jeez, right, so we've got here... we've got, I'm bad at me flowers. What would you call these?
Flowers.
Flowers.
I chose them randomly because I just wanted something to be completely random.
I like them. So we've got 4 flowers and a leaf is 33, and 3 flowers and a leaf is 26. Yeah. And above it, we've got the kind of algebraic representation of those simultaneous equations.
And I think if I remember when I asked them to solve that bit first, when we did this with the teachers, and they pretty much all to a man did the same thing. And I know they're all trained and highly qualified and brilliant secondary maths teachers, not one of them spotted something that children see. So they all did 4x minus 3x y minus y.
So I'm seeing 4x plus y equals 33, 3x plus y equals 26. Immediately, simultaneous equations, I'm going to subtract the bottom one from the top one, and that's exactly what I'm going to do straight away.
And of course, I don't give that to young children. I just give them the pictures.
Okay.
And the thinking skill there is what's the same, what's different. And what you're leading to there is this idea of difference and subtraction.
Okay.
So they'll see this is the same, this is the same, this is the same, this is the same.
And I noticed you've lined them up. This was something that we talked about
you're
before.
trying to, always with scaffolding to start with,
Yes.
trying to draw their attention to
Yes,
this, okay?
yes,
And
yes,
I might
yes,
even
yes.
talk about that. So, okay, these are all worth, so a flower's worth the same thing, a leaf's worth the same thing as that leaf,
Yep.
and so they represent numbers.
Yes.
The important thing is that when doing algebra or whatever, this isn't a flower, it represents a number.
Yes.
And same with the cups.
Yes, yes.
The unknown isn't the blue cup, it's the number of things in there. So that's an important point. And so why is this one worth more than that?
Because, it's got
Yeah,
the extra flower. The only
so very
difference.
young children, reception and nursery, I've done some things like this with, can see what's the same, what's different, particularly if you line them up. Okay, so what conclusion, what deduction, not trial and improvement, do we lead to from that?
So that must be causing the difference
Yeah.
between the two values. So the flower must be worth.
Yeah, which is what you're doing when you do your formal procedure there. When you subtract, you're finding actually the difference.
But I'm not thinking, right?
No,
So
you're not.
I'm
And this is
just-
what. And I want to make children who think mathematically, not just do it, but actually think in a way. Visualization.
Yeah, that's nice.
And what none of the teachers see is, can you see this in here? Can you see this in there?
right,
So in
okay,
here, we've got our three flowers.
Yeah.
Okay. And it's a different way of looking at it.
Yes, yes,
But
yes.
because it's visual, children see that,
Yeah.
and adults who've been drilled on that
absolutely.
and drilled too don't see that. So what you're doing is elimination, subtraction.
Yeah.
What they also see is substitution. They see that this in here.
Yes.
So this is replaced by 26.
Yes.
And they arrive at the same point, but it's a completely different way of looking at it.
Got it. I like that.
Yeah?
I like that. I'm there.
And you said everything's positive.
Yeah.
I don't really run out of time to answer your other question. The other thing that gets done in scaling, well, I hope I brought Chris Bolton's equation because I chose his at the end to finish with.
Right, okay.
Because it's like, that was his aim, so I show you how
Yeah,
I do that
cool,
as well.
cool.
I hope I've got it. Right, so the other thing it's about scaling equations. We teach children to multiply equations up and divide them down.
Okay.
I don't think children really get that. I think it's a process they don't fully understand. So what have we got here?
So
We've got...
Okay, 4 flowers and 2 leaves are 26.
Yeah. Now, again, I've set it out in a way to try and help them.
Yeah.
So here we've got 4 flowers and 2 leaves, and 4 flowers and 2 leaves.
Yes.
And they need to see that 4 flowers and 2 leaves and 8 flowers and 4 leaves is just this
2
one
groups
in
of it.
here.
Yeah.
So that's the scaling up.
I like that.
Yeah.
Yep. I'm happy
And
with that.
I got a lot to say on that, but I haven't got time today about how we scale up addition, subtraction, multiplication, division. We don't really
It's good.
spend enough time on that.
We're teasing people for a sequel
Yeah.
to this, Bernie. I like this. Keeping them wanting more. I like it.
And then we've got this
So what
one
have
I've
we got
set
here?
up.
So we've got 6 flowers and 2 leaves are 48, and then below we've got 3 flowers and 1
Yeah,
leaf. So if we see the 3 flowers and 1 leaf as being part of that,
Yeah.
it's half of that.
Yeah, and also the flowers have been halved and the leaves have been halved. They
halved,
both
yes.
have to be halved. These
Yeah.
are important
Of
properties of things
course.
that we
And again,
skip over.
there'd be potential to chuck a non-example in there.
Oh, yeah,
to show them something that they couldn't deduce
Yeah.
from that.
No, I'd always put that in.
I like it.
This is just for teachers, my quick one.
Yeah. So now we're getting a bit more complex.
Okay, so do you want to read that?
Yeah,
one out?
so we've got the formal way is 3x plus y equals 22 and 3x plus 3y equals 30, but then we've got it, which is fairly challenging, but then we've got it represented as 3 flowers and 1 leaf is 22 and 3 flowers and 3 leaves are 30. So I'm looking at this now and I'm thinking to myself, I mean, every fibre of my being wants to just go to the formal algorithm. I just can't wait to get going on that. But I'm looking at this and I'm wanting to kind of cover up things. I'm wanting to say, well, I can match up the 3 flowers are the same and each got a leaf in there. So I know that the only difference is the 2 leaves, which must represent the difference between the total. So I can see straight away the leaves 4.
Yep.
Yeah.
So that's one way of solving it.
Okay.
Okay, can you think of another way of solving it? This is another thing we do a lot of. Can you tell me?
And this is why I struggle, you know, Bernie. So again, I'm very much set in my ways here.
Yes, I know, yeah.
So let me think. So I don't know if this is different, but I could replace that with 22.
Yeah.
So I could take the 3 flowers and leaf
So you're
knowing
basically
it's 22, so I
substituting
can
it in.
substitute
Okay.
it,
And these are all ideas that I'll be building on with
Yes,
formally.
yes.
And there's one other way of doing it. Clue this one.
Oh, so the clue's so that one they halved it.
but it's not halving it. So in here we've got the same number of x's and y's.
Oh, okay.
So we've got those two, and those
So you
two,
kind of pair,
and those
yes.
two. So each pair must be 10.
So you pair up your flower with a
Okay.
leaf.
So if two, and I'll draw my flowers like that. What have we got? A flower and a leaf in each one?
Yeah.
Okay. So if a flower and a leaf is 10,
Yeah.
then that's 10.
Okay, and then we're good to go from
And,
there, yes.
and that's what I'm trying to encourage all the time is people will learn procedures, and it's very important that they do. But in the introductory phase, we have a look at different alternatives, which are going to be used later on.
Yeah.
In Chris Bolton shows, it's year 9 or year 10, I think
Yes,
it was,
yeah,
about
that's
multiplying up. Well, I'm doing scaling down, and I've done this stuff with year 4 children.
And I'll tell you what, like, my first instinct when I see something like this is, I don't have time to do this. Like, I've so much to get through. But you're absolutely right what you said before. The amount of time that this saves in the long run, because kids don't get simultaneous equations, or it looks like they're getting it.
Yeah, but they're not.
And they haven't got a flipping clue. It doesn't take much to screw them over.
I think that was the big thing out of the John Holt book, How Children Fail, is that it looks like children are doing things, but often when you dig around, they're really not. And then it's like, oh, what's the bit missing?
It's either they're just performing, or they can just do a specific type, right?
Yeah. So here, I want children to think mathematically, realise they can reduce that equation and do an x plus y is 10.
Yes.
And then play around with that. And they can then use it to that one and find the difference, or they could substitute it in here.
Yes, yes.
And then, of course, I do all that drilling thing about we take each type and drill that, but I would be looking at it this way at the beginning.
Okay. Now, at what stage do you want me to ask the big 2 questions that I've got spinning around in my head? Because I can see now how we can develop this for lots of different equations where everything's positive. The negative one is well, I have two biggies. You can choose which order to tackle them. The one is, how on earth does this work when you've got negatives?
Yeah.
And the second one is, how or when do I move kids to a formal way of solving them? Which do you want to tackle first?
I move to a formal way when I could do that with young children, but I would probably be doing that with older children. That would be my introduction. And at the same time, I'd be moving to formal methods. Because like working with the counters, okay, so if we express this algebraically, when we divided our little flowers there into 3 equal groups, how do we express that algebraically here?
Right.
So we're dividing across by 3. Everything's only that. So I would then move very quickly onto that.
And would it be the case of you're solving one of them using, so take that flower and leaf example, you'd solve that, we'd have that discussion exactly as we'd have. Would you then straight away represent that algebraically, so they've got it, and then move to another flower and leaf
I'd do
thing,
flowers first of all. I'll actually do cups, then flowers, and then start to work on the abstract form. But for me now, you see, when I now look at simultaneous equations like that,
so, oh geez, okay,
I'm thinking that as I do the algebra there.
Right. So
we didn't finish that time. We ran out of time.
Sure.
But
so you're always thinking in.
I can't help it.
Visual way.
Yeah.
All right. So you're.
So give me an equation.
So the answer to that question was that you would you're doing the algebra. You're kind of bringing it in there, kind of alongside, so they can see the kind of 2 different representations, and it kind of becomes the fact that they no longer need to kind of rely on the picture.
It's perceptual variation to get a concept to really understand what they're doing, to abstract that into a set of procedures and routines that they need to do.
Yes.
But with some understanding that if you ask them to draw that, they could actually draw it and explain it to you exactly what's going on.
Got it.
So that's the way that we teach everything. So I've just tried to apply that to algebra and try and show you that 4-year-old children, 5-year-old children, 6-year-old children can do this.
Right, okay.
So now hit me with a killer one.
So I'm going to, I'll do one that comes up nice solutions.
Yes.
But I'm just going to have just one negative sign in there.
So we need to start with nice ones, and then we have to move on into the abstracter ones that don't work out nicely.
Right, okay. So this will be a big, quick test of my mental arithmetic here. So let's go. I'm going to keep my solution secret here. Hold on. So this will be, I'm going for 3x plus 2y equals 22.
Yep.
And I'm going to go for x minus y. Will that be okay?
Yeah, whatever. Yeah. Maybe minus 2y to start with,
Okay.
so it's exactly the same, and we'll
Yeah,
do it step by
Yeah,
step.
fine. So x minus 2y. Oh, this will be embarrassing when this doesn't work out.
I get it wrong all the time.
I'm going for -6. So 3x plus 2y equals 22.
Do you want to double check that you're all happy with that?
Let's gamble. Let's
Okay.
gamble on it.
Okay, so for me, not flowers now,
Okay.
but a picture of this is, and I could use algebra tiles. And I'll just explain to you what I'm thinking.
Yeah,
this is
please,
how I'm
please.
visualizing this.
So we've got 3x tiles and 2y tiles, and they're 22. And then we've got an x tile and 2 negative y tiles is
Yeah.
-6.
Okay.
Okay.
So, what do I see? I see 2 0 pairs here.
Right, okay, because you've lined them up, so we've got the y on top
Yeah.
of a negative y, y on top of a negative y, so you're seeing your 0 pairs, which references back to the negative numbers, okay?
Okay, so
So
let's not even talk about adding and
No,
subtracting.
no,
Let's just
you're
talk about
seeing four lots of the
Okay,
x.
so you're seeing 4 x's. Yeah.
Yeah, nothing else.
And you're seeing what's 22? I'm imagining 22 and -6, which is 16.
I was hoping it was 16, yeah, for this one.
And then if the 4 x's are worth 16, I can
So you
deduce
can
that that's
get
4.
Yeah, okay.
Okay.
Right, I'm happy with that. And then what would it be? Would it be a substitution back
Yeah,
into
and then
finding?
I now know that this thing here is 4.
Fine, so we've
So
got
literally
put
in
it
the
back
drawing I
into
do that
any,
there.
Any of them.
So having
sold
done a
me
lot
on
of
that,
this
you've
work, when
sold
you
on
look at
that.
that, they go, oh, so there's 0 pairs, so let's just put them together, which we can call addition.
Right, I'm sold on
So in
that.
all of these problems, the children are either putting the whole thing together, which we didn't really cover today, which is addition, or they're looking at the difference between them, which is subtraction.
Okay, I'm happy with that.
Yeah? So that's the first one.
So what happens when they're
Now,
not?
come on, give us the killer one next.
So all I'll do this time is I'll make a different number of
Yeah,
y's.
yeah,
Okay,
yeah,
all right,
yeah.
all right. X plus 3y equals -7. 2x take y equals 7. So the only difference here, so we've got a couple of things going on. We've still got the negative sign, but now we've got a different number
Okay.
of
So
y's.
instead of looking at that representation, let's look at it in this representation.
So you've got the x tile or disk, and 3 y's are equal to -7.
And
Yep.
then over here,
2 x ones, and then one negative y one, and that's equal to 7. Okay, cool. Yep.
So basically, is some of the strategies we've been using so far is that maybe we'll put them together,
Okay.
or maybe we'll find what's different there.
Okay.
Okay, so is that going to be successful here? This is about making decisions.
So we can see like
There's
we've
a
got the
0
0
pair there,
tile,
that's looking good.
but then we're still going to have,
Yeah.
we're still this concept of unsolvable. We've
Yeah.
still got 3 x's and 2 y's
Okay,
that we don't know.
so how do we go about sort of making this picture look a lot better like the other pictures?
I don't know.
All right, so what I need to do is to have more y's down here.
Yes,
More
okay.
negative y's.
Yes, okay.
And now this is where this principle of scaling comes in.
Yes,
You can't just
okay.
plonk another by
Of
there. So
course.
what you're doing is scaling up. You want to scale up this part of the equation.
Yes.
So to understand this, and there's a lot of maths behind this, you have to scale up everything. So we're going to have, I'm going to change this bottom picture to this.
So you've added another 2 pairs
Yeah,
of
so I've scaled it
x's.
times 3.
Scaled it, okay.
And I'm going to scale this by 3.
Yeah, okay.
And I'm going to scale this by 3.
Okay.
Yeah?
Yeah, I'm there.
And now we can see that's gone.
Yes. Yes.
And we've added
And now
these
we
together
can
because we put them together. So it's when children, if they practice it with drawing, this is a pictorial element first, and then look at this, I'm thinking about why isn't this working? Because these are not matching up. I don't have some negative pairs. I don't have 0 pairs, sorry.
Yeah.
So I need to change this to 3, and then you have to understand about how does that work? Well, it means you need to change that to 6, and you need to change that to 21.
So,
And we do not do enough in this
No.
country about how to scale things up. How do you scale up 3 plus 4? What do you just double? Suppose you want to double something. Just double that one? How's that working for you?
Yeah.
Oh, no, actually you have to double them all.
But
How do you scale up 3 times 4? Well, you only scale up one of them.
and it's
And these bits are missing from our teaching, I think.
and it's these concepts that for this to be successful, it relies on the concept of 0 and 0 pair
Yes.
being absolutely
Yeah,
solid.
yeah,
with the
you're right.
kids.
It's
which isn't something that gets emphasised. Certainly at secondary, I don't think. But scaling as well, like,
Yeah.
God, that for me is a passing comment.
Yeah, I made
It's the key
tweet
to it.
Yeah, I did a tweet on that the other day, and I probably presented it very badly. And somebody said, "What are you talking about?" Yeah. And it's like there are structures, things underpinning maths that we do not teach, and neither do they in Singapore. That I think are missing, that are critical, and if we did teach them, our children wouldn't have the problems that they're having.
And just so I can just get my head around this,
Yeah.
you would go through it this way,
Yeah.
and then kind of after that, but with this still visible, show the algebraic representation of it.
Yeah.
So they're getting kind of both,
Yeah.
and then
Yeah.
kids at different times will be ready to kind of move
They
across.
they move when they're ready. And if you're doing an intervention, you might go back to the concrete,
Yeah,
but it's
yeah, yeah,
important
yeah.
to have a concrete or visual to go back to rebuild every time when they haven't quite made that abstraction.
I think I'm there. I think I'm there with this.
And what's interesting, you can do this with much younger children than you normally do it, because it makes it accessible to them. So all I've done is apply the same principles we apply to very young children to how would I try and get the ideas across with older children, but also, more importantly for me, is because I had to get guys into competitions and scholarships, is how do I get them to think mathematically, not just do procedures?
Yes.
How do I get them to think?
See, I have a million questions going around in my head about different topics, but I'm going to leave that as a teaser, save that for more, because I'm thinking, well, what's he doing for linear equations? What's he doing for this? What's he doing for ratio? Blah, 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 blah.
Oh, yeah, ratio. I used to spend months teaching that, and I discovered double-sided counters, and now I can teach the whole thing in 10 minutes. Literally.
Please, Bernie, don't leave me a teaser like that. Well, we'll definitely have to come back for more for that.